today I'm here to talk with you about cloud-native applications with Kubernetes. I know that the session was titled Cloud-Native Java, but I had a discussion with Josh Long, and I think it was much more appropriate for me to be talking about cloud-native applications because I'll be talking about applications in general and how can we be truly cloud-native in this new world with these new technologies that we have in 2017. My name is Edson Yanaga. I'm the Director of Developer Experience at Red Hat. My Twitter handle is @Yanaga, just in case you want to follow me. I share a lot of content about DevOps, microservices, cloud-native applications, domain-driven design, Java, and other interesting stuff, at least in my point of view. And I'm also a Java champion and a Microsoft MVP, and I work for Red Hat, which I think is the coolest possible combination, which just means that the world has changed a lot. And for me, I've been an open source advocate ever since open source was defined. So I'm very happy to be talking about Java and open source things, and to be here representing Red Hat to be talking about this subject. And I want you to give a tip. I just recently released a book from O'Reilly, Migrating to Microservices Databases. I just had a backup session that I presented this morning at noon. And I have like 50 hard copies that I'll be able to distribute and sign just after the session. I'll be at the Red Hat booth to sign them. So if you want a hard copy, maybe you can stop by the booth, but we have limited copies. So, well, hurry if you want any of them. So, but if you, just in case you want the ebook is available for free on this big URL, but if you don't want to type everything, there is a bug in our website. There is no direct link from the landing page. But if you type developers.redhat.com/books, you'll get an index of the books that we have available for download, and mine is on the list. So you'll be able to get an electronic copy of that at least, right? And I always like to start my sessions with this quote from Forbes. Now every company is a software company. You don't work for a bank, you work for a software company. You don't work for an industry, you work for a software company, because software is changing the world that we live. And some people call that digital transformation or digital economy. And just to give you a brief explanation what economics is, I'm used to be one of these people that thought that economics had everything to do about money, but then I realized that after studying a bit of economics, that economics has nothing to do about money, but has everything to do about people. That's why economics is a social science. We're basically studying people's behavior. And when we're talking about economics, we're studying how people interact with each other to change a system from one state to the other. And people have some motivations to change this system from one state to the other. Some of these motivations can be love, can be hate, can be power, and can also be money. So basically, we're studying people. And when we're talking about software, it's always important for us to remember that software is made by people, for people. Every time we forget that, we don't have an optimal result. And if we want to maximize the changes that we make into this world, of course, we have to remember that. Some great examples of this new digital economy, this new way of how software is changing how people interact with each other, are that the largest car transportation company in the world owns no cars, which is Uber. The largest lodging company in the world owns no real estate, which is Airbnb. The largest online retailer in the world owns no stock, which is Alibaba. And the largest content network in the world produces no content, which is Facebook. All of these companies, they have something in common, that they only exist because of software. So software is changing the world. And I also like to introduce myself as a software craftsman. I think it's a very nice opportunity, because I think that tomorrow Sandro Malcuso will be here. He's a Brazilian too. And he will be talking, I think, about software craftsmanship. I consider myself a software craftsman too, and the best definition that I have of a craftsman is somebody who cares about what he or she does with his duty. And I think that our duty is that we're supposed to leave a better world for the people that are living in it, for us, for our children, for the people that we love, and for the people that we don't know. So we should always care. I truly believe that absolutely no innovation is going to happen in the next 1,000 years without a software developer behind it. So we can make we can change people's lives for the better, but we can also make them miserable. And we know that because we feel miserable when we're using software that is not up to our expectations. And some years ago, I was in a very hard moment in my career. I even was thinking about giving up of developing software, but for the better or for the worse, I realized the only thing that I knew what in my life was to do software, so I would better do it properly. And I didn't want to make people feel miserable. I want them to feel better, to improve their lives. That's why I kept developing software. So that's my message. And since we're talking about cloud native applications, I would like to start with a discussion about some misconceptions that I've seen in the software world. First, discussion is if I create a fat jar, I'm doing microservices, right? Or maybe not. Okay, that's a big discussion. But what I like to say is that I love fat jars and I hate them too. It really depends on your deployment pipeline. And Kent Beck, I believe that once he said once that any smart answer to any non-trivial question always begins with "it depends." So, are fat jars or are thin wars better for my scenario? It really depends on how you handle that. If you want to copy a single artifact over the network and you're deploying like on-premise artifacts into your customers, maybe a fat jar is a better approach. But if you're in the world of containers, if you're using, it doesn't matter which infrastructure layer you're using. If you're using an application server, or if you're using Node.js, or if you're using a Ruby server, it doesn't matter because containers changed a lot of things. So people are just deploying their application servers like in a Docker layer and just deploying their thin wars with just the business logic is on the last layer. So it changed a lot too. As I said, it really depends on how your software deployment pipeline, how this pipeline, how does it handle your artifacts. So if you have a sufficiently mature software deployment pipeline, if you're already into containers, maybe it doesn't make sense for you to be copying the same artifacts over and over again in a fat jar. Maybe it's easier for you to just change the business logic. And I'm pretty sure that we can have this discussion in another moment, but the answer to this question is definitely no. Microservice has nothing to do about, and fat jars or thin wars, they're much more related to the kind of deployment artifact that you want to have in your deployment pipeline. So it has nothing to do with microservices. It's not a pre-requirement. You can do one with the other or vice versa. It doesn't matter. Second point, if it's good for Netflix, if it's good for Amazon, it's good for me, right? That's what we call cargo code, and in the software world, we call that cargo code programming. I don't know how many of you are aware of the term cargo code. Cargo code used to be that in some tribes in the Pacific during the Second World War, they realized they needed to establish some bases in the Pacific to fight the Japanese. Well, my far relatives. And so the Americans needed to establish some bases, so they had to buy the support from the locals. And since they were mostly non-civilized tribes, suddenly their people, they started to receive some ships, some planes, everything else, and they were bringing like goodies. They were bringing food, they were bringing medications, they were bringing gifts for them so they could be peaceful instead of fighting them. But then when the Second War ended, these tribes, they kept thinking, well, we don't receive any gifts anymore, no more food, no more medicine, nor anything else. We don't receive ships anymore. We don't receive planes anymore. So they started to build like huge landing zones in their islands. They tried to reproduce the control towers. There were some people with flags trying to signalize. They were trying to repeat the same things that the other people were doing and to check if they could achieve the same results. But for some strange reasons, the planes never showed up. They never landed in their new landing zones. They never received any more ships, everything else. So, in fact, they still do that on some islands as of the current moment. So that's what we call cargo code. Just because somebody is doing it, working for them, we are doing the same thing because we expect to have the same results. That's what we call cargo code. And when we apply cargo code programming, just because that company or that team is using that process with that technology, just by using the same thing that they're using, we will achieve the same results. What I'd like to say about that is that, Again, context means everything, and it always depends. What do you think about that? Very few companies in the world, they have the same scalability requirements that Amazon, Netflix, or Google have. So, like more than 80% of the world, of the software developers in the world that develop enterprise software. Enterprise software companies, they have completely different challenges. I don't want to minimize the problems that Amazon or Netflix, they have in their business, but I'm pretty sure that any enterprise domain model is much more complex in what they have. They have different sets of challenges, but modeling the business model properly in enterprise companies, it's a very, very hard task. So we have different sets of problems to be solving. But when we're discussing microservice architecture, again, I'm one of these people that believe that microservices is not for everybody. So maybe some people are trying to find a solution in microservices when they don't even have the problem. Now we have problems with monolith. Now we want to use microservice. Now we don't have a problem anymore. We have 10, we have 20. We have much more problems. So context is really king when you have to choose your technologies. But if you decided that microservices is your thing, that microservices will solve the problem that you have when trying to release software faster into production and more safely, then we need to consider how are we solving the problems that the distributed systems and microservice architectures brings to our world. Some of these problems, we have a whole list of problems that distributed systems brings to the table. I just chose 5 because these ones I think are the easiest to grasp and the ones that we have more tools, or at least the tools are more well known in the developer community. So think about centralized configuration, distributed tracing, service discovery, load balancing, and circuit breaker. Centralized configuration, because if you have multiple artifacts running in your system, then you don't want, I want to know which is the current state of my configuration in my system. I don't want to be checking to each one of my artifacts which is the current state to know what is happening in my system. Maybe I need a centralized point to check all of the information, all of the metadata of my system to check, well, this bug is happening because I have these current states. So centralized configuration is a requirement for microservice architecture. Distributed tracing, you used to have, if you had a bug, if you have an error, you used to have a stack trace when you had a monolith. Now you don't have a single stack trace anymore because your request can pass through a lot of different artifacts in the distributed system. And how do you correlate that this stack trace correlates to this stack trace that I have in this other microservice? So you need some sort of way to know each one of your business requests. Where does it pass through? And how do I correlate this transaction here from this transaction here? So you need distributed tracing too. Distributed tracing too helps you to solve one of the hardest problems in distributed systems, because if you have a distributed system and it's failing, okay, it's kind of easy for you to spot where the problem is. But if your system is low, it's very hard for you to detect which point of the system is making your system to behave slowly. So distributed tracing helps you to spot where is this low, or where is the bottleneck of your system. Okay, distributed tracing. What else? Service discovery. You used to have only one endpoint in your system. Now you have multiple, and each one of your different endpoints need to locate other endpoints to complete just a single transaction in your system. So you need some sort of service discovery. So your artifacts must be able to announce themselves to the rest of the world, and the other endpoints must be able to consume this new endpoint that entered the system. So you need some sort of service discovery too. Load balancing. We used to think that, well, we only need to add a load balancer or a proxy in our architecture. Then we have multiple different endpoints. Then this proxy will just load balance the request between the different backend points. But then realize that, well, maybe we have clients with different latencies. Maybe we have clients connected through different networks. Maybe we have some clients in a remote data center. And maybe have multiple services being hosted in different data centers too. So we have different latencies, different throughputs, different availability scenarios. Then maybe server-side load balancing is not enough. Maybe round-robin load balancing is not enough. Maybe we need to add some client-side load balancing. Maybe we need to add some kind of smart routing to our applications. Maybe we need to route Maybe users that pay a premium to our service, they should be routed to the fastest servers. Users that pay a very low price for our service, they could be routed to the less powerful service. That's some of the things that we can think about when we're talking about these microservice architectures. We have completely new challenges for load balancing. And again, circuit breaker, I'm pretty sure that everybody that has been discussing microservice architecture or has ever used the Netflix OSS has tried some Hystrix code, which is basically a distributed try and catch. I try to connect to that endpoint. If it's not available, I'm not allowed to propagate this failure to the other endpoints. I must handle that by myself. I must provide a fallback. So I'm trying to queue in that point. If that's not available, maybe I need a secure S that is stored, which can be a cache in my own microservice. So if I try to reach that endpoint, I try to get the data from customer 1000. Oh, the endpoint is not available anymore. Then maybe I already have a cache information from 10 minutes ago. It's better for me to return the maybe outdated information than propagating 500 error to the other endpoints. So circuit breaking is one of the things that we must take care when we're talking about microservices architecture. And how we used to do that, well, at least how many teams are trying to solve that. If you think about, traditionally you have to solve in your system, you have the business logic, which really depends on the business you're running on. And if you decided to choose microservice architecture, you have to solve at least these 5 problems, okay? Business logics and distributed system problems. And if you think about how Netflix created their OSS stack in 2007, which means like almost 10 years ago, they didn't have anything to build upon, okay? They had nothing. So they were facing some challenges. We want to create a distributed architecture, but now we need centralized configuration. Okay, there's nothing in the market. We need to create our own. We need distributed tracing. We need to create our own. We need load balancing. We need to create our own. We need service discovery. We need to create our own. And they were doing all of that on top of like AWS. So it's a very opinionated approach of how you should be solving this problem. Because if you remember how AWS was 10,000 years, 10 years ago, not 10,000. 10 years ago, it was very unreliable. Today, you can achieve much more reliability between AWS, but 10 years ago, it was very unreliable, okay? Machines could go down at any time. You could have network failures and all of the things. If you ever been a AWS beta tester, that's the scenario from 10 years ago. So they had to do what? The Netflix scenario is that they wanted to use cloud computing. They had these problems. So for them, solving tracing, load balancing, centralized configuration, circuit breaking, everything, that's part of their business because they had to build everything from zero. So Netflix solved all of these problems, including their business logic, in one piece of code. Okay? So if you think about, if you ever try to use Hystrix by hand, take a Hystrix commands and just type of that, you can see that you're mixing this kind of circuit breaking code. You have our business logic, you have your circuit breaker, and then you have the fallback logic. Everything gets mixed up. That's how they solved this problem, and that's how they've been doing that from 10 years ago until today. Okay? But we think how technology has changed in the past 10 years. So maybe in 2017, we have a different way to approach these problems. Maybe we have enough technology today to try to solve these problems in a different way. So maybe if you think about centralized configuration, distributed tracing, yada yada, these are, I believe, at least for me, I believe they are all low-level things. I shouldn't be dealing with that with business logic codes. And if you think about, for example, I love Spring Boot. I love the Spring Cloud stack. I think they had a very beautiful job integrating the Spring framework with the Netflix OSS stack. But before my job at Red Hat, I used to be an independent consultant, and I visited many different teams trying to solve that. And when they wanted to have a distributed solution, of course, the first solution, well, you need to use Spring Cloud and everything else. But then you were choosing, well, If I have a REST endpoint which is calling another REST endpoint, I'm going to create a method to query that, but I also need a fallback. Then I'll add a beautiful notation for the fallback methods. And then if my class should have like 4 methods for each one of the RESTs requests, then now I have 8. Then my classes start to get big. Then everything I did, I needed a magical notation. I need a lot of code to be solving that problems. And at a given point, like 2 years ago, I realized, well, it's starting to get bulky. Now I have to worry with all of these distributed things and my business logic at the same time. It's hard for me to know, well, business logic, fallback, and everything else. Sometimes you miss the right annotation, and something blows up in your face, and it's very hard when you have more than one endpoint to work with that. Then, again, isn't there a better way, like 2 years ago, and now even 2017, to be solving these problems? I think we should all move all of these problems that we're talking about to a layer below application layer. So it's clearly it's not a transportation layer issue, but if you think about the OSI layers, maybe it should be in a layer above transportation layer and below the application layer. Okay, so what are the tools that we have today to be solving this? But before I give you like a possible solution to this problem, I need to add more context to this solution. So again, context is king. Think about the big picture. How are we handling our deployments these days? Because in the past, we had a single server to do our deployments. Maybe you are advanced enough, you're already doing blue-green deployments, so you can do 0 downtime deployments on that. But in this new distributed world, in this new microservice world, it's very likely that if you're thinking about microservices, you're already containerizing your applications, and you want to run these containerized applications in a cluster, because you're not putting all of the eggs on the same basket. You're not running all of your containers as a single host. Maybe you're running your containers in multiple hosts, in multiple data centers, because you want failover. Maybe you want your request to be served by the closest server too. So if you're thinking about microservices, these are some concerns that I'm pretty sure you're thinking too. So we have different problems, and you need an orchestration platform to be solving this, right? You're not orchestrating your containers by hand. We used to do that in the past, but of course I think it's almost impossible for a human or a team of human beings to be orchestrating that manually. So probably you choose a container orchestration platform to be handling all of these low-level requirements. And I think that one platform that has become quickly de facto standard for container orchestration as a container orchestration platform is Kubernetes. So let's try to think how are we handling some of the deployments and how Kubernetes can solve many of the problems that I've discussed of microservice architecture, but not all. We need something more too. So these days, we don't do only blue-green deployments. Maybe we have a sufficiently advanced scenario. We are already doing canaries. Okay, so if you're doing canaries, then we don't have one instance of my microservice running. We don't have 2 instances. We have multiple instances running. If I have canaries, I have the ability to specify that, well, I want at least 3 instances of my microservice running in my infrastructure. If I want to do a canary, I'll create 1 new instance, so I have 4. Then maybe I'll issue a certain amount of requests to this new canary. And if the canary survives, then I can just drop one of the old instances. Then I can do that again to 1 more instance and everything else. So I can do some kind of canaries. Maybe I can do some kind of rolling upgrades too. Maybe I can do some smart canaries. It's not for everybody too. But that's some of the possibilities that we can have, for example, in a container orchestration platform such as Kubernetes, which is the subject of another talk. We'll not be discussing that today. So basically, I assume that you have a cluster of nodes which are running your application for high availability purposes, and for you to be able to handle these beautiful scenarios of multiple instances and canary deployments and rolling upgrades and everything else. So this is a current scenario of how we deploy our applications into production. And if you do that, how can you solve these other problems of microservices architectures? Or how can a platform like Kubernetes and OpenShift, how can it enable me to solve even more problems than just plain deployments. So I'll have to dig into some concepts of Kubernetes for you to understand what I want to say. So basically, if you're containerized applications, traditionally you have a container. You package your application and your environment in a beautiful container, and you're using that to run your applications into production. Okay? Then Kubernetes doesn't orchestrate containers. Kubernetes orchestrates pods. I don't know how many of you had this difficulty, but I'm not a native English speaker. And when people were talking that, oh, Kubernetes orchestrates pods and yada yada, I had a hard time understanding, well, why does it use pods instead of containers? But then somebody told me that, well, pod in English is the collective of whales. So if you think about pod is the collective of whales, it's very easy for you to understand, well, in fact, when we're talking about pods, we're talking about a group of whales, or if you think about a group of containers. So Kubernetes orchestrates pods. And into each one of pods, you have at least one container. Usually that's the most common scenario, you have just one container, but you might have more than one container into each one of your pods, and all of the containers on the same pod, they have the same life cycle, okay? They are started up again, they die again, and Kubernetes also checks if the pods are healthy. So if any of the containers on the pod is failing, Kubernetes considers that, well, this is a failing pod, I need to kill it, and I need to start another instance because they asked me that I need at least 3 instances of this pod into production. So if any one of them dies, I need to start a new one, okay? That's some basic prerequirements. So if you think about that any pod can have more than one container, maybe we could have a pod in our hosts, and we can have in this pod, we can have a container which contains our application, and we can have another container which we will call a sidecar container, which is just an ancillary container that provides us some functionality which are not related to business logic, but maybe this side container can solve some problems for us, just like load balancing, just like circuit breaking, just like tracing, or everything else, right? Maybe you can use sidecar containers for that. And it's very cool because, well, maybe if I'm going to instantiate a sidecar container to be solving load balancing, but what if the sidecar container dies? If it dies, Kubernetes considers the pod to be not healthy. It will kill and restart another one with the 2 containers on it. So maybe it's a very safe solution for that. Another concept that Kubernetes has is what we can use some daemon sets, which we can ask Kubernetes, well, each one of my hosts in the systems, it needs to be running one instance of this pod. And this pod could be like a solution, again, an ancillary application that can handle some aspects of distributed systems like load balancing, distributed tracing, on behalf of my applications, okay? This is the discussion that we're having currently in the distributed system world. How can we solve all of that problems that I was shown to you, load balancing, circuit breaking, service discovery, and everything else? How can we solve that in another layer? And the discussion is, can we solve this problem with sidecar containers, or can we solve this problem with node proxies? And I have seen people with very strong opinions advocating for sidecar containers, so with some strong opinions advocating for node proxies. And I've discussed it with some teams that are using that into production, and I clearly can tell you that there is no winner so far, because again, it all depends on context. If you want to think about some companies that are using these kind of solutions to solve real-world problems, for example, Spotify released Linkerd, which is the solution that they use to be solving all of these distributed system problems. They created a solution that mainly behaves like a node proxy, but can be used too as a sidecar container. So they handle that. I don't want to be handling circuit breaking and load balancing in my code and tracing in my code. I want to delegate that to a proxy. So what their application does, instead of your application issuing requests directly to the endpoint, your application issue request, for example, for Linkerd, and Linkerd deals with the load balancing, with the circuit breaking, and everything, and tracing, and then issues the request to the remote host. Then it gets the request back and goes back to application. So your application code can be business logic only. You don't have to worry with all of these things. So you basically, either with sidecar containers or node proxies, you are adding a proxy to your application, okay? So sidecar containers can act like a proxy, and a node proxy, which proxies all of the requests of your host, can also act like this proxy and add this kind of capabilities, right? Sounds like a good idea, but think about other problems that we might have in these distributed systems. Imagine if in a microservice architecture, you won't have a single instance of each one of your microservices running. Then imagine that I create a microservice, and this microservice, this blue microservice, needs to issue requests to my green endpoint, okay? Which doesn't matter which service it is. But if I have like 4 instances running in a certain host, all of them are issuing requests to the green endpoint. And if you ever used something like Hystrix or Ribbon, to be Hystrix for the circuit breaking and Ribbon for the client-side load balancing, you might wonder, for example, for Ribbon, for the client-side load balancing, it measures the latency and the throughput for each one of your endpoints, and it chooses the one that performs better for you. Isn't it kind of obvious that for the same hosts, all of these microservices for blue endpoints, they will have the same data from routing, right? Because the green endpoint is always the closest one for the same hosts. Shouldn't they be sharing this kind of information, or should they be queuing every time that? We're thinking about only 4. But imagine if you have a huge host running on Amazon with, I don't know, a terabyte of RAM, and you have lots and loads of microservices running. All of them, if you have 100 microservices running, 100 of them will be issuing requests just to query the exactly same information, right? And if you're doing circuit breaking, imagine here, if all of these 4 blue microservices are issuing requests to the green endpoint, if the green endpoint is failing, isn't it like agreeable that if it's failing for one endpoint, and if that's the same request, all of the requests from the 4 microservices will be failing? Okay? But if you use traditional Hystrix, which handles that in the application layer, each one of your microservices will have a different count of failures from the remote host. But in fact, it would be much better handled if they could aggregate the information. Okay? That's some of the things that we must be thinking about when trying to solve this problem. So these are some of this discussion, for example, where sidecar containers wouldn't solve either, because each sidecar container would have its own data of how many failures or how is the latency. So for the load balancing thing, I would have replicated data, and we could have a shared data for all of that, because that's the same, exactly the same information. We could be saving money and time, memory and time. And for the case of circuit breaking, maybe it would be much better if you could aggregate all of the failures of the microservices. So if you're thinking about a microservices circuit breaking strategy, you get Hystrix, for example. You can configure that, of course. But suppose that you configure your Hystrix instance into each one of these blue microservices to say, well, if a certain endpoint gives me 5 consecutive failures, I consider that endpoint to be failing, and I want to open the circuit for that, right? But each one of your blue microservices would need to fail 5 consecutive times for it to be considered open. But if you have like another entity, like a node proxy, which is represented here in red, if the 4 microservices are issuing requests to the same green host, then the first 5 consecutive requests, doesn't matter which microservice was issuing that results into a failure, they would already open the circuit. So you would have much less failures in the overall system. This is one of the discussions that we're having right at this moment to try to solve this problem, okay? So some solutions, if you think about Netflix OSS solves that in the application layer, and some companies are thinking about that for some time, quite actually. How can we solve that in a layer below? If you think about that, I think that's the new generation of middleware. In the end, you used to handle transactions and persistence, everything in the application layer. But when the technology evolves, when it matures, we don't want to handle that in the application layer anymore. We want to move that to an application below. We used to have to handle thread pools. We used to have to handle transactions. We used to have to handle messages and remote communication and everything else. Then some people decide to create the concept of an application server, which is a layer which we used to call that middleware, which solved all of these common problems. We standardized that, and we create something called an application server. Consider this kind of problems for distributed systems, for microservice architecture, to be a new layer or the new application server, in the sense that it's a new layer that we're adding on top of our infrastructure. We don't want to handle that as application code. We can handle that as infrastructure layer or middleware layer. Some of the common names that people are giving to this new kind of thing are node proxies and service mesh. If you think about service mesh, they're talking about these kind of solutions and try to solve that. But instead of just plain talking, I want to show a demo of how can things behave. And I just talked about Linkerd, but Red Hat recently committed itself to be supporting is not the right way. We are directing some efforts into to the Istio service mesh, which is based on top of Envoy, which is a sidecar container solution provided by Lyft. So these are probably the most popular solutions that we have in the market today. We have Linkerd, which is a cloud-native computing foundation project, which was created by Spotify and donated to the open source community. And we also have Envoy, which was created by Lyft and was donated to the open source community. And now we have companies like, for example, Google, Red Hat, and IBM, which are working on top of Istio, which is a service mesh solution that uses Envoy as a sidecar container. So I think these are the most popular solutions that we have in the world now. Of course, they integrate very beautifully with the Kubernetes platform, but you don't have to use Kubernetes to be using these capabilities, even though I believe that it wouldn't make much sense to use these things if you don't have a container orchestration platform. And why is that? Well, I'll show that in the demo. So you're not seeing anything because I didn't mirror. Now you do. What do I have here? I have a cluster of containers running in my machine. So, well, it's a bit sluggish, and the fan is very noisy right now. So I have a very different host, and I have some fake endpoints, and some of these fake endpoints are supposed to fail the request. I think in about 40 or to 60% of the requests, it is supposed to fail. Okay, so I have some healthy endpoints, and I have some failing endpoints, and I'm issuing the request for them, and I'm proxying all of my requests to these failing endpoints in my cluster with Linkerd. Okay, so these statistics are being provided by Linkerd, but Istio and Envoy, they provide the same exactly functionality. I'm just using Linkerd because that's the demo that I had running in my machine. And if you think about that, this layer, just like application servers used to be handled by the infrastructure guys because you had some configurations to be messing around, it is still a bit hard for you to configure properly this node proxy or sidecar containers. So maybe that's the task for the ops guys, at least for now. So it took me some time to set up these things. So what do I have here? I just have the circuit breaking capability of Linkerd being shown up on this demo. What do I show? I have here, I have some clients, some client microservices issuing some requests to some endpoints. Some of them are healthy and some of them are failing. Okay? In a traditional non-cluster environment, usually you would have only one instance of each endpoint. So Linkerd and Istio and Envoy, it doesn't apply to that, because if this one is failing, there's no other one for me to be routing the requests. But if you have multiple instances, you can pretty much assume that, well, I'm trying to connect to this instance, it is failing, I want to remove that from my request pool, and I'm wishing the subsequent request to the other endpoints, because the other ones are healthy. But if you think, well, if one of them is failing, it's very likely for me to have all of them failing. That would be true if you didn't have things like canary deployments. So companies like Spotify, they do canary deployments a lot. They just release a new version of your service, and they have the older versions running too. So if that one is failing, if the old one is failing, you can, if the new one is failing, you can automatically remove that from your request pool and just issue requests to the old version, which is completely fine into production. Okay? And with traditional histories, for example, which solve things in the application layer, the best you can do is that, well, if I have 5 consecutive requests which are failing, then maybe I want to remove that and want to get to the fallback. The best thing, just configure here the circuit breaking functionality. So here, the first scenario, the first graphic, if you see, I just configure that just like history would behave. And you can check that for my endpoints that are failing, the general availability or general success rate of my invocations are running in about 95, 94% of availability. And that's the best that I can achieve with what do I say, a default strategy for circuit breaking. So the best availability that or best success rate that I can have with a default circuit breaking strategy scenario is 94, 95, sometimes more, sometimes less. Sometimes I can get 93% of success rate, which for some companies, it's not enough. Again, I'll mention the Spotify case. Maybe for Spotify is not enough. Maybe for Netflix is not enough. But if I think about a solution as a node proxy where I can have much more sophisticated circuit breaking functionality, for example, here on this graph, I'm showing you the consecutive failures. So maybe in the next, I can configure different parameters. Instead of just using fail fast, well, 2 consecutive failures or 1 consecutive failure, I want it to remove it from the request pool, maybe for 5 ones, maybe for 6, or maybe 6 in the next 20, or this kind of things. For here, I again have a consecutive failure rate of 5. Here I can sometimes achieve 100% of success rate, but sometimes it can drop off to 92%. It's a different strategy for secret breaker that Linkerd has available. But what I really want to show you here is this one, which is probably the one that they're using to production, which is the success rate. I'm just saying that for a remote endpoint to be considered healthy, in a set of 20 requests, at least 90 or 0.9, 90% of the requests to that endpoint must be successful. So that's probably the one that they're using in production. If you think about the success rate of my applications, if I use this strategy, I can achieve most of the case 100%, but when things go very bad, I can have a 97.934 or nearly 90-80%. But on average, the goal is to have 90% availability, and that's what they can achieve using a node proxy like Linkerd, which they couldn't handle using an application level solution such as Citrix, because the statistics is distributed between multiple endpoints. If you concentrate all of your data in a node proxy, you can have a much smarter solution for circuit breaking. So this achieves a much better success rate or a much higher availability than using a traditional solution. And the same thing, you can do that for circuit breaking. You can assume that, well, you have much lesser load if you're using solutions like Envoy or Linkerd for load balancing and everything else. Okay. And these are some of the concepts that I wanted to show today. Don't be scared of that, because that's the discussion that we're having these days. Many of the solutions, they are entering the enterprise space of how enterprise companies can use this startup or this unicorn solutions into the corporate world. So expect much more discussions. I particularly believe that 2017 is the year that we're gonna find the best practices of how can we use this kind of solutions into enterprise marketplace. And when 2018 will be the year where we'll be deploying this kind of things into production. We have some companies already using this kind of solution, but it's not widespread. So people are thinking about using that. But in 2018, I think we already have the best practices for how can we use the solutions in the enterprise world, okay? For now, what I've seen is a few enterprise companies are trying that, but they are being effectively used in unicorn companies, as I said, like Lyft, like oh my God, Spotify and other kind of companies, okay? I said that multiple times. And that's what I wanted to show you today. If you want to have more information, we'll be discussing a lot about this subject on our blog at developers.redhat.com. I would love your feedback on your session, and the best way to reach me is at my Twitter at Yanaga or my email yanaga@redhat.com. And thank you very much. Okay. I think we have 5 more minutes for questions. Anybody has any question?
With the node proxy solution, you're not adding a single point of failure there?
I'm not load balancing the...
With the node proxy solution,
okay.
You're adding a single point of failure.
Yes.
So how do you deal with that?
Well, exactly, that's one of the downsides of using a node proxy, because if you have the sidecar container, Kubernetes will just restart the whole pod into this host or into another host, depending on your strategy for container scheduling. Some of the discussions that, yes, it's a single point of failure. If I have a node proxy in my host and it fails, then I could assume that all of my requests on that host should be failing too. So maybe that's one of the discussions. There is no clear solution for that, because if you get into the expert lists that are discussing this kind of solution, maybe one of the solutions that if you have enough number of nodes in your cluster, maybe if a node proxy running as a daemon set is not working properly, maybe the entire host should be considered unavailable, right? Then all of the pods that are running that, they should fail over to other hosts. That's one of the discussions that they're having right now. And as I said, 2017 is the year that people are trying to uncover the best practices of using these solutions. And this is an active discussion. So far, the best answer that I have is that, well, if a node proxy running as a daemon set is not working properly, maybe if you have enough hosts, maybe that host should be considered unavailable. Okay?
Thank you.
Thank you.
Thank you. Hi. My question is, the original solution from Netflix solving these problems at the application level, and also the problems that you are solving with Linkerd, many of them come from the fact that the messaging for the microservices is using HTTPF transport, and some of these problems may be solved with more classical messaging platforms, and in fact it's starting to be mixed, the responsibilities or the capabilities of Linkerd with those of messaging systems. Don't you think we are reinventing the wheel again?
Okay, well, it's a discussion about synchronous requests, if we can use messaging. What we've learned from experience is that, again, messaging systems requires you to use asynchronous practices in your code. And I don't know if I have to say, unfortunately, most of the enterprise developers, they're kind of comfortable in their way of thinking of just using synchronous requests, because imperative style, synchronous requests, it's easier for you to think. Maybe it's easier to solve the problem. I truly believe that most of the problems that we have could be better solved using distributed and asynchronous messaging. But I have to be very honest, that's not the most widespread concept in our industry. So we are using this kind of solutions, and it's not restricted to HTTP. It's protocol agnostic. You could be using to any synchronous protocol, or even distributed messaging, because even the broker could fail, right? You could use these things for the message broker protocol. So what would I say is that it's not tied to synchronous requests, can be used for message brokers as well. But the most widespread solution when people are discussing microservices, fortunately and unfortunately, are synchronous requests. So that's why I focused my discussion here, tracing and everything else for synchronous requests, because that's the most widespread concept. And I don't think it's bad, because if you have low scalability requirements, few requests, if you can deal with some sort of cache on the client side, maybe synchronous requests are good because they're easy, right? It's easy to think, easy to implement, fast usually. But then if you have, for most, I'm a domain-driven design advocate. I like the concept a lot of using domain events to be solving many of these problems. Of course, I advocate for distributed messaging. But again, I said, it's not as widespread as we wanted to. And for this kind of solutions, we have, this kind of problems, we have this kind of solutions.
Thank you.
Thank you. And I don't think we have time for more questions, but I'll be available the entire conference. And again, muchas gracias.